I'm terribly sorry for that. I just realized that when Dr. Azrina was texting me about the tutorial question for graph algorithm. So so I was like, oh my God, is there a lecture this week? So I seriously just realized, I think they changed it. I don't know why, but somehow I kind of like have it in my calendar that that week is actually the midsem, but somehow I don't know whether it has changed or what. But yeah. Um. So again, huge apologies for that. I saw few of you actually uh, came into the teams. Uh, Unfortunately, nobody tagged me to remind me that there's actually a class. I seriously like thought that it was actually mid-sem at that time. Okay, so my apologies for that. Okay. All right. So for today, we are going to be doing the lecture that we missed. And then for the graph algorithm part two, we're going to do asynchronous and the tutorial as well. Okay, we're going to do the asynchronous tutorial. I still owe you the tutorial feedback. I guess I'm going to do for this tutorial and pass it to you as soon as possible. Okay. All right. Anyway, I did give you some good one afternoon. Okay. I better start recording. All right. So before we start, do you have any question that you want to ask, class? Don't tell me you're still in the Raya mode. Class?
Questions in terms of
any question regarding your group project or anything, or maybe we can keep we keep it until we finish the lecture perhaps, or maybe from the previous lecture. We haven't had any lecture for 2 weeks, and my brain is also like a little bit still muddy. But yeah,
okay.
yeah. Mm-hmm.
If I'm not mistaken, and this is about the group project. This is actually just one of the problems in the group project, and I just want to ask.
Okay.
If I'm not mistaken, problem one has asked about making a route, doing like plot a route kind of deal. Does it mean like follow the road, or do we just use like the what's it called? The grid?
The
No, not
straight
grid
line.
circle. Yeah, straight line. Do we follow the road, or do we do a straight line, or is it?
Okay, so since the question is actually regarding the ground delivery, so preferably use the road. Try to use the distance according to the road. Okay, so yeah, I would prefer you to actually use the distance of the road rather than the straight line.
Okay.
All right. Okay, so again, I'm terribly sorry about the confusion. I seriously somehow I already planned like, okay, during that week of Raya there's no class, so yeah. But anyway, we're gonna cover that lecture today. So for today's lecture, I'm going to be doing a video, so you can watch it when you can. And I saw somebody like give you the give the code for attendance. Did you sign that one? Class?
Yeah, we did.
Yeah.
Okay, then I don't have to create a separate attendance for that. I'm terribly sorry. I don't know how come. I seriously thought like from the beginning of the session that I know that during the week of Friday is supposed to be your midsem. I don't know whether they change it or I mistakenly, because I remember discussing with Dr. Azrina that during that midsem break is actually Raya. Anyway, Okay, so today we're going to be looking at lecture 10, which is graph algorithm. So if you remember the last 2 weeks, we covered a topic called the greedy algorithm, right? So do you still remember what is greedy algorithm? It's a very straightforward, simple algorithm. Do you know what is greedy algorithm used for? Basically, class, you still remember?
Optimization.
Yep. So greedy algorithm is normally used for optimization. So what can you talk about the approach of greedy algorithm? What are the concept of greedy algorithm? You still remember? Find the best solution at the current stage. Yes. Okay. So basically, we try to find what is the next best local decision at that point of time. Okay. So that is basically the concept of greedy algorithm. So that you can find what is the optimal global solution. Okay, even though sometimes, yeah, perhaps greedy algorithm may not give you the most optimal solution, but at least it will give something like an approximate of how you can get the the optimal global solution. Okay, because as we can see of the knapsack problem, some of the situation we cannot apply greedy in order for us to get the most optimal global solution. So later on, I think after graph algorithm, we're going to be looking at dynamic programming. Normally for optimization, dynamic programming can do better, okay, in terms of optimization, but that is just that it requires more computational power rather than you apply the greedy algorithm where you just keep finding what is the next best solution at that time. Okay, but then we're going to be looking at dynamic programming after graph algorithm. Okay, so most probably next week we're going to be looking at dynamic programming. Okay, so for today's lecture, graph algorithm, we are going to be looking at greedy algorithm, okay, used to solve graph, used in a graph algorithm. Okay, so we're going to be applying a greedy algorithm inside this graph algorithm, okay, to find the solution, the solution. Okay, so here we're gonna have two parts. So basically today we're gonna be covering part one. Okay. So part one we're going to be looking at terminology, you know, in terms of what is graph and so on and so forth. Acyclic graph, how you can do the graph representation, okay? What does it mean by connected components? We're going to be looking at some graph algorithm. Okay, we're going to be looking at some elementary ones. Okay, breadth first, depth first, topological sort, and then we're going to be looking at minimum spanning tree. Okay, whereby we're going to be looking at two algorithm called the Kruskal and Prim's. So in part two, so this is the one that I'm going to be doing the video on. Okay, asynchronous lecture for part two, where we're going to be looking at more graph algorithm. Okay, single source shortest path, Dijkstra algorithm and Balmer-Ford, and then all pair shortest path, Floyd-Warshall and Johnson algorithm. Maybe I will be covering one of the Balmer-Ford and Dijkstra. All pair shortest path. We will see if we how do you call that? If it is not too long, then I'll be including the Floyd-Warshall and Johnson algorithm as well. Okay. All right. So first of all, you know, like we have used graph in a lot of application. Okay, so for example, you know, when you want to model the connectivity in computer networks, okay, representing maps, you know, the location and so on and so forth, modeling capacity in networks, finding path. Okay, so if you are doing some AI software, you probably need to how do you call that, represent the nodes and path. Okay, you can use graph, and then you can use graph to model transition. Okay, in algorithms, graph can also be used to represent an ordering of tasks. Okay, so let's say for example, first task, second task, and what should come before, what should come after, as well as modeling relationship, okay, such as family, organization, your social media, the connection, friends connection. So you can actually represent all this stated here using a graph, okay. To look at the terminology of what is a graph, we can say that a graph consists of vertices, okay, as well as edges. All right, such that you have an edge that connects between a pair of vertices. So basically, you have vertices, two vertices, and you have one edge connecting the two vertices. Okay, the number of vertices, okay, you can is written as such. You call it modulo, right? Modulo v. Is it modulo? Yeah. And then the number of edges is written in this notation. Okay, the number. All right. So for the two vertices that are neighbor, they are called adjacent to one another. Okay, so any vertices that are adjacent to one another, they are neighbors. Okay, and they are joined by an edge. And then if let's say you want to represent an edge connecting two vertices U and V. So if let's say I have this is U, this is V, we can write it as this one. Okay, so we're going to say that it is UV. All right, and then sometimes for your edge, okay, you can also have a cost or weight. So let's say for example, you want to say that these have a value of 5, let's say for example. So you can have a weight on on your edge, okay, that connects between the two vertices. Okay, so imagine if you have a map. So this is the first location, this is the second location, and this would be the distance between the two locations. Okay, hint, this is something related to your project. Okay, all right. So a cyclic graph is a graph without cycles. Okay, so a directed graph without cycle is called directed acyclic graph, or DAG. So basically you can say that a free tree is connected undirected graph with no simple cycle connected with d minus 1 edges. So okay, let's say for example, you have a graph. So you should basically this kind of graph, there is no cycle, and you can say that oh sorry, this is typo, sorry. This is a simple cycle connected v minus 1 edges. Okay, so if let's say you have a free tree connected, maybe a tree is normally looking like this. It's supposed to be undirected. Remember, we used tree before in our heaps and so on and so forth. So in a sense, a free tree that is connected, undirected graph, we know simple cycle. We can say that it has v minus 1 number of edges. Okay, so if let's say 1, 2, 3, 4, 5, 6. So basically we have 6 vertices is equals to 6. So the edges will be 5. Okay, so 1, 2, 3, 4, 5. Okay, so that is how you will view a graph. Okay, when you talk about vertices, edges, this is what these are the concept of a graph. Okay, a graph without cycles, and the number of vertices, normally the edges would be the number of vertices minus 1. Okay. All right. Okay, so how do you represent a graph? You can either represent it using directed representation or undirected representation. Okay, so if you notice just now, I draw one graph with arrows and one graph is without arrows. Okay, so you can have either directed graph or directed graph or undirected graph. Okay, so both methods can be represented either using adjacency matrix, okay, whereby you create an array, or you can also create the adjacency list. So it's something like a linked list that you can create to represent the graph. All right. This is a few examples of graph representation. So here in A, you can see graph A. This is an undirected graph. Okay, so you see the edges are not directed. Okay, and then for this graph, this is a directed graph. Okay, and you can see the arrow. So you know that it is a unidirection edge. And then you have labels, okay, associated with the vertices as well as the edges. Okay, so this is a labeled graph or weighted graph. Okay, so you can also have so you can label your nodes, okay, as well as weight, put a cost or weight for your edges. Okay, so these are some of the graph representation that you may have. Okay, so what does it mean by connected components in a graph? Okay, so in an undirected graph, you say that it is connected. You say that there's at least one path from any vertex to any other. Okay, so if it is a connected graph, you can get from one vertices to another. Somehow you should be able to find a path from one vertices to another. So that's why if it is a connected component, you can do that. So if like, let's say for example you want to go from 2 to 3, you can go through this path to get into node number 3. Okay, so that is what you mean by connected component. Okay, and if let's say this is not a connected component because you cannot get to 7. Okay, there's no path to go to 7. And the maximum connected subgraph of an undirected graph are called connected components. Okay, so if let's say you have this, you would say that these are just the connected subgraph. Okay. Sorry, excuse me. Okay. Sorry, I hear something from outside. Okay. All right. So let's look at how you can represent a directed representation for directed graph. Okay. Okay. So let's say we have this graph. Okay. So this is a labeled graph with labeled directed graph. So we can represent it using adjacency matrix, or we can represent it using the adjacency list. Okay, so let's see, as you can see here, for the adjacency matrix, we somehow create like some kind of array, okay, multi-dimensional array, whereby we have we label this side the columns and the rows as the name of the label of the nodes. Okay, so if let's say we want to represent node 0 and it is and its adjacent neighbor vertices. Okay, so we look at 0 here, and we put 1 to at any node that is connected to node 0. Okay, in this case 0 is connected to 1, 0 is connected to 4. Okay, so therefore for 0 we put 1 under 1, and we put 1 under 4. And then the rest, we can put it as 0. Okay, so this is how you represent it using adjacency matrix. So let's look for the next node. So let's say, for example, we want to see at node number 1. Okay, node number 1 is only going into node 3. So we put 1 under 3. Next one, if let's say we look at node 2, 2 goes to node 4. So we put 1 under 4, and so on and so forth. So that's how you create the adjacency matrix for representing this directed graph. Okay, this directed graph. Adjacency list is basically you create a list, okay, of what are the adjacent vertices that is connected to that vertex. To that vertex. Okay, so let's say, for example, we have 0. So we have 0 going to 1 and 0 going to 4. So we just put 1 and we put 4, okay, as one list. And then same goes for 1. 1 only connected to 3. So we put 3. 2 is connected to 4. So we have 2 connected to 4, and so on and so forth. This is how you create an adjacency list. Okay. So let me see. Okay, maybe I will mention it later. Okay, this is for directed graph. Okay, so for undirected graph, concept is still the same. It's just that for undirected graph, okay, let's say, for example, this one between 0 and 1, this is an undirected graph. You can either go 1, 0 or 0, 1. Okay, so it's bidirectional. So you can go 1, 0 or 0, 1. So therefore, in your adjacency matrix, for vertex 0, you can go to 1 and you can go to 4. And if you see, for vertex 1, you can also go back to 0. You can also go back to 0. Okay, so it's bidirectional. You can either go, it can go both ways. Okay, same goes for if you want to create the adjacency matrix. It's the same thing. Okay, so you look at vertex 0. What are the adjacent vertex that is connected to it? Okay, so for in this case, this is 1, this is 4. Okay, and then for 2, we have 4 and 3. For 2, we have 3 and 4. And you can also hear 3 is also connected to 2. It goes back to 2. All right. So basically, that's how you create the adjacency list. Okay. All right. So basically, between these two representation, okay, whether the adjacency matrix or the adjacency list, for the adjacency matrix, the good thing is that in order for you to how do you call that, find a node, to find a node, the running time complexity is order of 1. But the bad thing is that you have to create this array, which will cost you big O of V squared. Okay, so basically this one, if you can see, this is a number of vertices. So if let's say, for example, you have 5 vertices. So basically, you're gonna have to prepare like 25 array. Okay, array space. But for adjacency list, the advantages of it is that if you want to add, it's pretty easy because it's just a list. But then, in order for you to find the number is a little, the element inside the graph is a little bit, I would say it requires some cost there. Okay. So therefore, if you look here, the differences between the cost of space. So for the adjacency matrix, as I mentioned, it requires more space. For the adjacency list, all you need is so basically the space you may only need is basically the number of vertices that you have as well as the edge, and you know that the edge is actually vertices minus one. Okay. Uh, yeah, so basically those are the reason why you can choose whether you want to represent your graph using adjacency matrix or the adjacency list. So it depends on this situation. If like, let's say for example your software requires a lot of finding a node, then perhaps adjacency matrix is much more appropriate because of the runtime complexity is constant. Okay, in order for you to find uh, uh, the nodes and so on and so forth. Okay. All right. Okay. Can you give me one moment? 1 second. Sorry, guys. Uh, wait, what? What did I press? A little bit busy day for me today. Okay. All right. Okay. So now we're going to be looking at an elementary graph algorithm. So this is basically you always basically if you talk about graph, um, um, you use this algorithm for you to do search. Okay, so if let's say you want to search the nodes and so on and so forth, so you can use depth first search or the breadth first search. Okay, so I'm sure you've heard about this before. So today we're going to be looking at how actually that the depth first search and the breadth first search is being conducted. Okay, so this is the pseudocode for the depth first search. All right. All right. So perhaps we can just straight away look into this example. So for depth first search, all right, we have to bear in mind that we are going to be using stack, okay, in order for us to run this algorithm. Okay, so we're going to be keeping two lists. Okay. Uh, so normally what you do is that you will keep a list of you will keep a list of visited visited node, as well as you need to have a stack. Okay, you remember what is a stack? So a stack is whereby first in last out, a stack. So I normally call it a stack as first in last out. Okay, so we're going to keep a list of visited and stack. Okay, so let's say for example we have this graph, right? So we have this graph. Maybe it represent, I don't know, maybe represent let's say for example you create a game, okay, whereby you a maze game, let's say for example, where you need to search a room, okay, where I don't know, maybe you want to find a treasure in one of the rooms. Okay, so these are the rooms that you have, okay, in the map. And these are the path to each of the rooms, okay. And then you want to make sure that you visited all the rooms in properly, okay. So basically you wouldn't want to miss any room when you want to search for that treasure, let's say, for example. Okay, so how do we do this is that, okay, so let's say we're going to be choosing which node to visit, alphabetical, in alphabetical order. So let's say we start with A. All right. So for that first search, what we're going to do is that we are going to be keeping a stack. Okay. A record of a stack. So let's say, for example, we visited A first. Okay. From A, we know that we can either go to E or we can either go to C. Okay. But since we want to do depth first search, we are going to select one of its possible path. Okay. So we're going to choose C. Okay. So we visited A. We're going to be visiting C. Okay. So we visited C. All right. And then from C, we can visit either B. We can either visit B, F, or D. And sorry, B, F, and D. Okay. So since I mentioned that we're going to use alphabetical order, therefore we're going to visit B first. So we're going to go C and visit B. Okay. So after we visit B, we're going to be looking at all possible path from there. Okay, so basically from B we can only go to F. So so since F has not been visited, so we're going to visit F. All right. So we're going to visit F. So from F, you can either go to C, you can either go to D, or you can go to E. But since again, alphabetical order, we're going to visit D first, and then we're going to visit E. Okay. All right. So therefore, that is how you create a path to do the search. Okay. And then since E, you cannot go to anywhere. Okay. So from E, all of the so basically E has wait, did I miss something? Oh yeah, correct. Okay, so basically this would be the wait, what I think I missed something. The stack. What did I miss? I'm so sorry. 1 second. Suddenly my mind went blank.
Doctor, why can we
Yes.
visit E through D?
Sorry, E through D. You cannot.
Yeah,
There's no
like
path.
because from F first we visited D, right? And then why can
Uh-huh.
we visit E from D?
Because there's no path from D to E.
Okay, okay.
Let me check. I think I missed something. Uh, wait. Suddenly my mind went blank. I really hate like after the command. Suddenly my mind went blank. Uh, all right. So Oh, okay. I missed. Yeah, I truly miss this one because just now when we visited D, D does not have let me backtrack. I think let me start again. I just because we forgot about the stack. Okay. Okay, let's start with visited A. Right? So we start with A. So we visited A. Since A can either go to E or C, we're going to visit C first because we're going to do it alphabetical order. So we're going to go to C. And then C can either go to B, F, and D. So we're going to go to B first. All right. And then we're going to go to B. And then from B, we can go to F. And since F has not been visited, we can visit F. All right. And then from F, we can either visit D or E. So since, again, alphabetical order, we're going to visit D. Right. And then D, basically, we cannot, D, we cannot visit anymore. So we can pop it into the stack. All right. So we can pop it into the stack and then we can take out this one. All right. And then after that, from F, we can visit E. So basically, we look at the visited. So we go back to F. And then from F, we can go and visit E. Since E has not haven't been visited, so we're going to visit E. All right. And then E can only visit A and F. And since A and F has been visited, we're going to pop E. We're going to put E into our stack. Okay. And then we're going to put, and then we're going to go back to F. We're going to pop F. We're going to put F. And then again, from F, there's no other way that you can go. And then you're going to put B. And then you're going to pop off C. And finally, you're going to pop off A. So basically, in order for you to pop out the output, you're going to get the output. You're going to pop out from stack, whereby it is A, C, B, F, E, and D. Okay, so basically how you search is that you go and look for the visited node. Okay, so if you have visited the node, basically you sort of like go back and then see what other node that has not been visited. Okay, so in this case, for that first search, the traversal of the graph looks like this. Okay, it will go A to C, C to B, B to F, F to D, and F to E. Okay, so for the depth first search, it is using stack. So if you look at the breadth first search, it is still using like looking at what is the edge, to choose the path. For the breadth first search, it's a little bit different because for the breadth first search, instead of using stack, it is using queue. All right. So again, we're going to keep a list of visited as well as the queue. All right, Q U E U E Q U E. Right? Okay. So we're gonna order. So BFS, we can say that what we're trying to do is that we're going to search level by level. Okay, so if let's say do a level by level search. Okay, so what we're going to do in BFS, so since we're going to start visit A, so we're going to visit A, and basically we can either go to so basically we can so first we queue A, and from A we can either go to C, or we can either go to E, right? This one. So A, either go to E or go to C. Okay. So since so we look at the queue, we're gonna DQ A first, and then we're gonna since the queue is not empty, we're gonna look at the next one. So we're gonna look at C. So C, you can go to B, you can go to F, you can go to D, right? So basically we can queue B, we can queue D, and we can queue F. Uh, uh, so so basically so basically we visited C. So so we DQ A, we DQ C. And since again the queue is not empty, we're gonna go and visit E. What is it doing? Oh my god! Every time I'm always like confused about this one. Uh, um, my god. All right. So where were we? So we visit. Sorry, I'm so sorry. So visit E. It's not E, right? It's F. What am I doing? I'm so sorry. My brain is a little bit scattered today somehow. Something happened in the morning, so I'm a little bit overwhelmed still. I don't want to go into that. Okay, so basically we visited A, all right? So we visited A, we visited A, and then we can so basically we Q A. What am I? Okay, we Q A, and then we can visit either C or E. So we can Q C and we Q E. So we visited A, and then we look at the queue. Since the queue is not empty, so we're going to look at C. Okay, we're going to visit C. So we're going to visit C. What am I doing? Oh my god. We're going to visit C. All right. And we're going to visit E. What am I doing? I'm so sorry. 1 second. A, C. Can I get back to you? These two, I think I missed something up. In terms of the stack and the queue, I think I mixed something up. Somehow my brain is not making any sense. So can I get back to you? I'm so sorry. Between these two algorithm. Okay, so I'm going to get back to you regarding this matter. So can we look at the topological sort first? Okay. So for the topological sort, okay, so for the topological sort, normally topological sort is like if, like, let's say you have an example, you have this graph, okay? So you have this graph whereby you can see here that for C to happen, you must make sure that A and F happen first, okay? So for topological sort, we want to make sure that the sequence of events or the sequence of tasks is being done according to the order of appearance, according to the order of required the time that it is required. So let's say, for example, you have a dependency, okay, in package whereby you have several packages, and in order for package C to work, you need to have a package A and package F installed. Okay, so that's why you need to do the topological sort. Let's say, for example, you have this. So how do you do it? Is that you are going to do DFS, okay, onto this, and then basically the sequence that you get in the stack will determine the sequence for this. Okay, so again, I'm going to get back to you with the DFS. Perhaps you give me like five later on. I'm going to like recollect myself for 5 minutes. Somehow my brain just went blank, just like like when you're exam and you are like have so many things in your brain and suddenly you cannot find it. So maybe perhaps later on, please just give me like 5 minutes for me to recollect myself. So I'm going to be revisiting this again. But basically, what we for the topological sort, this is what we are trying to do. Okay, so basically, we want to try to find the sequence whereby we want to make sure that whatever node that comes before it, or the nodes that is being required to be available before it is clear. Okay, so basically we can for you to do topological sort, you apply the DFS, and then the stack that you get from the DFS algorithm, you're gonna get the sequence. Okay, so the stack will show you will give you the sequence of which node should come first before the next node. Okay, and you will see that the topological sort will depend on how do you actually apply you choose which node to go first, so you may get a different topological graph. Okay,
Uh,
so sorry, yeah.
so is it technically possible to do like wait A B G E F? Is it possible to put like F all the way at the front instead of A B G?
All the way to
Like
the
start off with
front.
start off with F and then A B G E C. That would technically be all
Oh
right,
yeah,
right?
yes. Because since F for F, uh, E and C, the only node that depend on F is E and C. So you can have F before A as well, or anywhere before. Is that all right?
Okay.
Yeah. So it is possible for you to have that topological graph as well. Okay. So again, as I mentioned, it depends on how you do the DFS. Again, later on, give me 5 minutes to just recollect myself, and I'm going to get back to you and explain to you the BFS and DFS. Somehow my brain just go blank. Okay, so this is another example, okay, of topological sort. All right. So if let's say you have this graph, and basically this graph, and you see they have already like given what is the start time and the end time for each of these tasks. Okay, so basically based from the end time, you can actually arrange the sequence of tasks uh, uh, um, um, to see which should be put on first. Okay, and so on and so forth. So you can have a different, like let's say for example, a different topological sort, but since this one it has given some time, so you will get this topological graph. Okay, for this problem. All right. Okay. Yeah, so we're going to be looking at minimum spanning tree. So can we take a break for like 10 minutes? I need to like
Uh,
use one. I need to go back and,
okay.
and recollect myself for that algorithm just now. Somehow it just go blank. I have no idea why. Suddenly went stupid. So I'll see you back at 4. Yeah, to
Okay, Doctor.
continue with minimum spanning tree. All right. All right. I think it's because I skipped my lunch today and my brain is not working. But anyway, okay. So I'm so sorry. Somehow I go blank a little bit. Just now. Okay. So can we start back? Looking at how we can do the depth first search. All right. So as I mentioned, when we do the DFS, we're going to be using stack. Okay. So what we're going to do is that we're going to create a stack whereby we're gonna keep. I think it's better to use this way. Actually, the other way is actually the new way. I want to clearly show you what does it mean by visited and not visited, so that we can. It is quite clear for you to see when we look into the topological sort. But anyway, so let's try and do this again. Okay, so if let's say we have this graph. Okay, this is an undirected graph, so therefore it can go either way. Okay, so let's start with let's say for example we start from vertex A. Okay, so for DFS we're going to be using stack, and so since we start with A, so we're going to visit A. We're going to pop A inside our stack. Okay, so from vertex A, you can either go to C or you can either go to E. So since it's the DFS, we're going to go D first. So we're going to choose either C or E. And in this case, we're going to be using alphabetical order. So we're going to go and visit C. Okay, so we're going to pop C into our stack. And we're going to look at C. From C, where else can we go? Okay, what are the adjacent vertices from C that we can go? Okay, so basically from C we can go to B, D, or F. So in this case, we're going to be choosing B. Okay, so we're going to go to B. So we're going to pop B into our stack. All right. And then again, we're going to be looking at B. What are the possible ways that we can go? So for B, there's only one way. We can only go to, we can only go to F, right? So we're going to go to F. So we're going to pop F in, right? So F, you can either go to D, we can or E. We're going to go to, we're going to go to D first, and we are going to pop D into our stack. Okay, so from D, we look at the adjacent vertices. So D can only go to C right now or F, and both of these vertices has been visited. So therefore, we are going to pop D. So we're going to pop D. All right. So after we pop D, we're going to go back to, we're going to look at F. So F, we're going to see if there is any vertices that hasn't been visited from F, and we found out that we can visit E from F. So we're going to put E in our stack. Okay, we're going to pop E into our stack. So now we're going to look at E. Oh, sorry. And now we're going to look at E. Okay, so E can either go to A or can either go to F, and both of these vertices has been visited. So therefore, we're going to pop E off. All right, and then we're going to go and look at F. Since F, same goes for F as well, we're going to pop F. And then we're going to look at B, and then we see B, same thing as well. So we can pop B off. And then we look at C, we can pop C off as well. And finally, we look at A, and all the adjacent vertices of A has been visited as well. So therefore, we're going to pop A out. So therefore, we have complete the search of we have completed the search of this graph using a depth first search. Okay, so the only thing that I did not keep is that just now what I'm trying to do is that I want to have a parallel whereby to write what are the visited visited nodes, so I got confused. So so this time I just focus on the stack. So basically, the visited is when you the sequence of vertex that you visited. So basically, just now we visited A, and then we visited C, and then we visited B, F, D, and E. Okay. So basically, you can look it from the stack as well. So basically, you pop out the you can read it from the stack as well. It's the same sequence: E, D, F, B, C, A. Okay. So that is how you do that first search. So for the BFS, okay, we're going to be using Q. All right. This time we're going to be using Q. So normally Q is like this, rather than like a cup. Okay, so again, we're going to start with A. So we're going to Q A. And basically, we go, so since A is not empty, okay, basically we're going to visit A. And from A, you can either go to C or E, right? So, so we look at the queue. Since the queue is not empty, we're going to dequeue A. We're going to look at A. So we're going to queue, so we're going to visit A, and we're going to visit C, and we're going to visit E, right? So, so A is done. And then we're going to look at the next one, which is C. Okay. So for C, you can either go to B, F, or D. So we can queue all this. We can go to B, we can go to D, and we can go to F, right? And we're going to visit all this first. We're going to visit V, we're going to visit D, and we're going to visit F, right? And then we're going to dequeue C. Okay, so we're going to look at the queue. Since the queue is not empty, we're going to look at E. So E, all the adjacent vertices has been visited, right? So if you look here, A has been visited, F has been visited. So we can dequeue E. Same goes for B. We look at B, all the adjacent vertices has been visited. We can dequeue B, and then we look at D, and since for D same thing happen as well, we can dequeue D, and finally F, we can dequeue F. And when the queue is empty, meaning you have visited all the nodes, provided the graph, all the nodes in the graph is connected. Okay, so that is how you do the BFS. Is that okay, class? I'm so sorry, I was suddenly, it just went blank because I was trying to keep the two lists together, so I got confused. But is this much clear to you? How do we do the depth first search and the breadth first search, class?
Doctor, so so for example, if at E there's like say another one G, another node G connected to E in breadth
Oh,
first
which
search.
one, yeah?
Breadth first
What?
search. B
Breadth
BFS.
first search, okay. All
So that
right.
means so we go A and then we go C. So we got the Q A C E B D F. And then we go to E. E has G. So that means
Oh, no.
after F we have G as well.
No. You will visit E. So like right now, since okay, since the search is completed when you basically when you go to C, you can start look from C, you can actually look, basically this one you can say that they are in the same level. So that's why we sort of like complete the B, D, F, and since F can be is also adjacent to E, therefore it completed. But let's say if like, let's say for example, can we okay, so if like, let's say we put G here, right? So what we're gonna do? So basically, just now when we finishes visit the C and we queue BDF, we dequeue this and we're gonna look at node E, right? So for E, E can either go to F, but since F has been visited, we are not going to queue F, but we are going to queue G back here. Okay, and we're going to basically visit G then. Is that okay? What? Because just now, when we do C, when we search from C, we actually already we can actually we search B, D, F first before we actually start looking from E.
So we basically finish everything under C first, and then move to
Since it's
the.
connected, yeah.
Okay.
Because since C, the adjacent nodes to C is the B, D, and F. Okay. So basically, in order for you to do the search, you use the queue. You follow
So
the
that
queue in
means-
this.
So that means once AC and then C goes BDF, and then we check B if there's anything else. See if there is more, then we get that into Q, and then finish all the way. And then after once everything under C is done, then we go to A, E, and then finish everything under E. If that is.
Okay, in terms of printing, for the queuing, yes, this is how you do the queue, because you will queue the BDF first before you queue G.
Okay.
Okay. All right, so that is how you do the depth first search and breadth first search. So the difference between that is the DFS is using the stack, and so and for the BFS it's using queue. Okay, so you have to queue your queue your element and then dequeue it after you complete the search. Okay, so for this topological sort just now, since I mentioned we need to use DFS, okay, so let's try to do DFS for this one and see whether we can get this topological graph. Okay, I may not get the same one because I forgot which sequence of element that I choose. But how you do it is that you apply the DFS onto this graph. Okay, and this time your graph is a directed graph. Same goes as the concept is still the same. Okay, so you have your stack. So you can just choose to start from any node. So let's say, for example, I start from, I don't know, maybe I start from F. Let's say, for example, okay. So I start from F. So I'm going to pop F into my stack. So so from F, I can either go to C or I can either go to E. Okay, so I can either go to C or I can either go to E. So normally I will use alphabetical order. I'm going to go to C first, and I'm going to pop C into my stack. Okay, and then C, there's nothing else we can do. So we're going to choose another node. Okay, so let's say, for example, so let's say, for example, I choose node E, let's say, for example. Okay, I'm going to pop E inside. So I'm sorry. So we need to pop out first. So we need to pop out first. So basically from C, there's no, so we pop out, and then we're going to pop in E. So from E, there's no adjacent matrix, so we visited E, but then there's nothing going on there, so we're going to choose another node. Okay, so let's say, for example, I choose node G. Let's say, for example, so I'm going to pop G in. Okay, so G, the adjacency matrix is E, so it has been visited. So we don't have to do that. So maybe next I'm going to choose A. All right, so I'm going to pop A in, and I'm going to visit A, and then I have either to go to B or go to C. So since the only vertices that I haven't visited is B, so I'm going to pop B in. Okay, so basically we can say that Basically you can I get a different sequence already. So from the stack you can actually create your topological sort. All right. So um we can have uh F, C, E, G. Oh, why didn't I get the what did I forgot to pop something out. I think I forgot to pop something out. When I pop, it's supposed to be the sequence. It's not the stack. It's the popping out of the sequence. I forgot to pop out the element when I pop out the thing. So therefore I didn't get the sequence. Okay, so basically the sequence you get from the stack. Just now, how come I get the thing from the stack, huh? 1 second. Um, so from F, we stack C. So C. So visited. So let's say we start from F, right? So just now we start from F. So F, we can go to C, we can go to E, and then we pop in C into our stack, right? No wonder, because I go and pop in F first. F is supposed to be visited. So this is the reason why I got confused just now, because when you do the topological sort, you need to keep track of the visited. Okay, so let me try and do this again. All right. So let's say, for example, we start from F. Okay, so we're going to be visiting F. So maybe I'll keep visited list. No, I don't want to reduce the visited. It's so confusing. So let's say, for example, we visited F. So from F, we can either go to C or to E. So since we again, we're going to pop C in first. Okay, so we're going to pop C, and then F we can pop from F, uh, 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 and then we're going to visit C. Okay, so F we visit C, and then C we and since C is not does not have any more not adjacent, but the path to the next vertices, we're going to go into E. Okay, we're going to go into E. So we're going to visit E. All right. And then so so I think we need to do the visited. Else it's not, we don't know how do we get back to the F. Okay. So let's start back. So let's say we start from, oh my god, I'm so sorry. Let's say we start from F. Okay, so we visit F. So we visit F, we're going to pop C into our stack. And then since C we cannot go anywhere, we're going to visit, so we visit C. And then after that, C is completed. We're going to pop C, and then we're going to go back to F. All right. And then we're going to visit E. Okay, so we're going to pop back. We're going to pop E inside our stack. Okay, and we visit E. And then after that, we look at our stack E. Again, E does not have any path going out from E. So we're going to pop it out. And then we're going to choose another vertices. So let's say, for example, we choose A. Okay, so we're going to visit so we're going to visit A, Alright? So we're going to visit A. So for A, you can either go to B or C, but since C has been visited, we're going to visit B. Okay? So we visit B. And we're going to pop we cannot pop B in yet, because from B we can also go to G. So from B we can go to G. Okay, so we look at G. When we visited B, we can go to G. So we're going to visit G. And then from G, all the vertices has visited. So we're going to pop G into our stack. Okay, so we're going to pop I forgot to pop F into our stack just now, since we cannot since F does not have any more vertices to visit. So now since G have no more vertices to visit, so we're going to pop G inside our stack. And then we're going to pop B into our stack, and finally we're going to pop A into our stack. Okay, so from here we can say that from here we can get the sequence. So we know from here the sequence should be A, B, G, F, E, C. Okay, so A, B, G, F, E, C. So if you arrange this in this sequence, you will see that you will get this topological sort. So you know that for here, you know that in order for you to do C, you need to do F and E first. Okay, or let's say for example E, you need to do G and F first. Let's say for example. Okay, so that is how you do the depth first search for topological sort. Is that okay? So actually, the reason why I got confused is because I want to relate the way that you do the one in topological sort by keeping track of the visit with the stack. So that's why just now I got confused. But is that all right, class? Or you're confused? Okay, so if you have any question, maybe we can try and look in our tutorial, because we have one question of topological sort in our tutorial. So we're going to look at that during tutorial. Okay, so same goes for this one, but in this case, since like you can get if we do not have the deadline, you can have any sequence of sort. So in this case, since we have the end value, we can basically arrange the sequence of tasks according to the end time. Okay, so you can get this example from the Commons book. All right, hopefully I got to finish this one off. But I think for the minimum spanning tree, it is actually fun. I like minimum spanning tree because the concept is quite fun, and it's quite easy to understand. Okay, the concept. So basically, a minimum spanning tree. So let's say, for example, I know I do not have like some kind of stop. So basically, up until now, we have looked at BFS, DFS, and topological sort. Okay, so these are these are algorithm that you can use onto a graph. Okay, so breadth first search, depth first search, that was for searching. And topological sort is for you to sort, if like, let's say you have a task or a package dependency, you can actually apply this algorithm to create a solution. Okay, so another application of graph algorithm is the minimum spanning tree. Okay, so let's say for example, you have a graph like this. Okay, it's a weighted graph, labeled and weighted. You can actually create a minimum a spanning tree. So what before we look into the minimum spanning tree, let's look at what does it mean by spanning tree. Okay, so maybe this is quite a big graph. So maybe I'll create a simple graph like with 4 nodes. Okay, like this. Okay, a spanning tree is any tree that connects all the vertices without any cycle. Okay, so like, let's say for example, for this graph, if let's say I have this graph, I can also have, let's say for example, I have this A, B, C, D, and this one is 5, 4, maybe let's say this one is 3, 6, 2. So a spanning tree, not a minimum spanning tree, a spanning tree can look like this. Okay, a spanning tree can look like this. A spanning tree can also looks like this. Okay, so basically what I'm trying to say is that you can have a spanning tree that looks like this because you have 4 vertices connected by 3 edges. Okay, so spanning tree, this the number of edges inside a spanning tree would be vertices minus 1. Okay, the number of edges. So in this case, you have 4 vertices. So therefore, inside the minimum spanning tree, you need to only have 3 edges. Okay, you can have this spanning tree, or you can have this as a spanning tree. Okay, or you can have maybe the is it the same? You can probably have I don't know, maybe this as a spanning tree. Okay, so when you talk about minimum spanning tree, okay, so if you look at the variant of spanning tree that you can get, and given that each of the edge have weight or cost, so if let's say I choose this as the minimum spanning tree, what is the cost? So the cost would be, so in this case, this is 5, this is 3, and this is 6. What is the cost of all the edges? It would be 5 plus 3, 8. 8 plus 6 is 14, right? So the cost is 14. How about this one? So we got 5, we got 2, and we got 6. So 8 plus 5, so the cost is equals to 13. So basically, whatever combination of spanning tree, we can actually get a different cost. So when we talk about finding what is the minimum spanning tree, we want to find what is the most smallest spanning tree that have the lowest cost. Okay, for that connects all the vertices with v minus 1 number of edges. Okay, so for doing this is where we're going to apply the greedy approach, okay? Whereby, in order for us to find what is the minimum spanning tree, we are going to grow our minimum spanning tree, okay? And how are we going to grow this minimum spanning tree? Is we're going to apply the greedy approach, okay? So, okay, so basically there are 2 algorithms, okay, for minimum spanning tree. Both algorithm applies the greedy approach. Okay, so basically in MST, the greedy strategy, okay, used to grow the minimum spanning tree by finding one edge at a time. So it's either you find the minimum edge or the next best edge from that vertices. Okay, and then basically you're going to somehow create a loop to grow your minimum spanning tree, and both algorithms have a different way of growing their trees, but in the end you're going to get the minimum spanning tree with your graph with the total number of edges v minus 1. All right, so basically how do you determine which edge to add into your tree? We call it a safe edge, and this is what the greedy algorithm is going to do for you, okay, which is to find what is the safe edge to be added into your minimum spanning tree. All right, so as I mentioned, there are 2 algorithms for this, Kruskal and Prim. Both of them grow their minimum spanning tree by finding what is the safe edge to add into their minimum spanning tree. So for Kruskal algorithm, you have a set A, a forest with vertices um, Okay, so for Kruskal algorithm, basically the maybe I can summarize between the prime and Kruskal is that for Kruskal we only grow one spanning tree. So basically, how do you add to a set of A, okay, of the spanning tree that you're growing, is that you are going to add one safe edge into that set A. Okay, and for Prim's algorithm, you're gonna get some set A. Oh, is it the other way around? For Prim's, is actually you grow one single tree. So whereby how you add the safe edge is you will add to you will determine all the edges that is connected to the tree itself. But for the Kruskal, you're going to look at the whole graph and try to create several branches, which in the end will form one minimum spanning tree. Okay, so I guess we're going to look at an example to show you a much clearer picture. Okay, so let's look at Kruskal first. So I'm going to go straight into the example. Okay, so for Kruskal, let's say for example, we have this, how do you call that? This graph, right? So in Kruskal, what we're going to do is that we're going to find what is the most smallest value edge in the graph. So in this case, which one is it? This one is the smallest edge, smallest value, okay, which is 1, right? So the next safe edge that we're going to add into the forest of spanning tree in order to find the minimum spanning tree, we're going to look at what is the next smallest next edge that have the smallest value. So anyone can let me know which edge that have the smaller next smallest value, class? Anyone?
FG.
So we have either IC or FG. Okay. So in this case, let's choose IC. Okay. And then next, since this one is not going to create any cyclic, we can choose IC and we can choose the GF. Okay, what is the next one?
ABCF.
So we have AB, we have CF. So so AB, since AB is not going to give you a cycle, so we can add edge AB and C as well, since CF is not going to create any cycle. So we're going to add CF into our forest as well. So what is the next best one? It would be which one? It would be IH and CD. Okay, so can we add IH into our spanning tree?
No.
Because
Yep.
we are going to create a cycle,
Cycle.
right? Yeah, so we cannot add this edge in, but we can add this one in because it's not going to create any cycle, right? All right, so what is the next best one? 7 and we got 8, right? So we got this 8 and we got this 8, right? So so can we add AH? We can add AH, right? We can add AH. So after we add AH, can we add BC?
No.
No, right? It's going to create a cycle. So we are not going to choose BC. So the next one would be which edge? It would be
D.
it's going to be DE. So DE, yes, it is safe to add into the tree. So next one after 9 is 10. So can we add EF in? No, right? Because we're going to create a cycle. So 10, and then we're going to try to add 11. Have we visited all?
Yes.
So we have visited all. So we can say that this is our minimum spanning tree. Okay, so you're probably going to get a different minimum spanning tree provided which edge that you choose. So for example, just now, in this case, just now I choose this one first, so I cannot choose this edge, right? So it depends on which edge you choose. So your minimum spanning tree may look different, but you're gonna get the smallest the minimum spanning tree for this one. Okay, so in this case, yeah, for this example, it chooses this one as well. So basically, this is the minimum spanning tree for this graph. All right. Okay, so that is for Cruskal. Okay, so basically what you do is you just find what is the smallest edge, see whether you can add, it is safe to add to the forest, and no cyclic. If it is no cyclic, then you just add it into the forest. And then basically in the end, you're going to get one minimum spanning tree, all connected, all connected. Okay, the edges are connected. You can get from one vertices to another. Okay, for minimum spanning tree. All right, next we're going to look at Prim's algorithm. So the difference with Prim's algorithm is that if you notice just now, what we did was, okay, so if you look here, we are growing the tree, and the tree is like not connected. So basically, you find one branches here, you find one branches here, and so on and so forth. But for Prim, you only grow one minimum spanning tree. Okay, so let's say for example, so I'm not gonna basically I'm just gonna skip the explanation and just go straight to the example. Okay, so let's say we have this graph. Okay, and then we choose to start with this node. Okay, so we start with this node. So what we're going to do is that we're going to see all the edges that is connected to that to that vertex. Okay, and choose the smallest cost, smallest value that is connected to that tree. Okay, so this has been added to the tree. So basically, A is already in a tree. So we're going to determine whether we're going to add this branch or this branch. So which one should we add? AB, right? Because AB is smaller than AH. So we're going to add this edge into our tree. Now, the tricky part is, now this is your tree. You are going to look at all the possible branches out of that tree. So basically, the consideration is this edge, and this edge. Do you see what is going on? Right? So out of these three edge, which one would you choose? Which one is the smallest? So it's either you add BC or AH, right? Oh, we have, right? So it's either we add BC or AH. So let's say we add BC. Okay, so we're gonna rub this one off. So, oh sorry. So we're gonna add BC in. Now this is a tree. We're gonna look at all the edges that is coming out from that tree. So so basically the edges that is we are going to consider is that this one, this one, this one coming out from C, this one coming out from C, and this one coming out from C. So which one are we going to choose? The smallest one, the smallest edge? It would be
CI.
CI, right? It's going to be CI. Again, we're going to look at all the edges that we can consider. So now since we have I included in our tree, so these are the possible edges that we can consider. So which one? Which is the next one? So we have 8, 11, 7, 6, 4, 7. So which one? Which one should we get? We should get
4.
CF, right? So we should get CF into our 3. So the edges that we can consider, this edge as well as this edge, right? So which one now that we can consider? So we have 8, we have 11, we have 7, we have 1, we have 6, and we have 2. Okay, no, not 1. Sorry. We have 2, we have 6, we have 7, we have 11, we have 8, 7 and 14. Which one? Which edge should we consider?
H2.
H2, which is GF, right? So we're going to consider GF. Sorry. So we're going to consider GF. Okay. And now the edges that we can consider includes this one. Sorry, the F. Sorry. And now F, we can also consider this edge, right? Okay. So which one is the smallest edge of all the possible edges here? So we have 8, 11, we have 8, 11, 7, 1, 6, 4, 7, 10. Yeah. Which edges that we want to add into our spanning tree? Class? Nobody? You're gonna add?
GH.
GH, right? GH has the smallest value. So GH has the smallest value. Okay, so right. So okay, so yeah. So basically these are the next all the possible edges to have. So which edge should we safely add into the minimum spanning tree now? Class?
CD.
CD, right? CD would be the smallest that would not create any cycle, right? So we have CD, and then we have this edge to also consider. So which one should we get?
DE.
So DE. So basically, we're going to get this added into our spanning tree. So this is your minimum spanning tree. Okay. So if you try to add the number, you're going to get the minimum spanning, the minimum cost for all the edges in this graph. Okay. Are you okay for this one, class?
Yes.
Yeah. So do you see the difference between those two algorithms to find the minimum spanning tree? Okay, and both of them are using the greedy algorithm. So basically, they try to find what is the next best thing in order for you to find what is the best, what is the most optimal global solution. So in this case, the greedy algorithm is able to actually produce the minimum spanning tree. Okay, so for particularly for this algorithm, applying greedy algorithm will get you the minimum spanning tree. Okay. Otherwise, how would you do it to find the minimum spanning tree? You probably need to calculate all possible spanning tree, right? That would take a lot of computational time for that. So basically, this is the best approach to find what is the minimum spanning tree. Okay, class. Any question about Prim's and Cruskal? This is quite nice. I like this. This is very interesting. So normally, for Prim and Cruskal, is quite interesting. This one. Class. Any more question for this one? we're going to look at graph algorithm part 2. So I'm going to create a video for that. Tutorial this Thursday, we're going to do a tutorial for this lecture. I'll try to figure out how are we going to do the tutorial for the next lecture. If let's say, for example, the dynamic programming, we can combine the two tutorial. Maybe perhaps we can just combine the graph and the dynamic programming tutorial together. Okay, because I think in week 13, this is week 11, right? Correct me if I'm wrong.
Yeah, correct.
11, so next week is 12. The week after that is 13, 14. So normally, since we are a big group, for my tutorial group, I have 3 groups. So normally I will open slots starting week 13, okay, for the Viva for group project. So hopefully you have somehow get at least like 50% of your group project done. I received a few issues from you, so I will try to address it afterwards. Yeah. So any question about your group project or this week's tutorial? I'm so sorry because just now my brain just went blank. Actually, I was trying to link it. Initially, the first way is actually the way I explained before, but since I want to, so that you won't get confused, and I'm the one confused because I was trying to explain it so that you can see that how the stack is connected to how you determine the sequence in the topology. So, but I end up getting confused myself. Yeah, so sorry about that. Okay, so if you have no more question, then I guess we end the class for today. If you have any question about your group project or any issues, I don't know, with your group or something like that, please let me know. Oh, sorry, I
Doctor, I have a
saw,
question.
yeah.
What is the weightage is negative?
The weightage is negative. That one we for the Kruskal and Prim, if I'm not mistaken, normally for Kruskal and Prim, we only consider positive weight. If you have a negative weight, there's a different algorithm that you can apply. We are going to be looking at negative weight, I think, in one of the algorithm in part 2. Okay.
Oh, okay.
Right.
Second question. What if there is no weightage?
There's no weightage. Then how are you? Then how are you going to calculate the minimum spanning tree? Or you can only do spanning tree or do BFS, DFS maybe.
Oh, okay. Thank you.
In this case, the reason why you apply the Prims and Kruskal is you want to find the minimum spanning tree, the smallest cost for connecting all vertices with V minus 1 edges. Okay. I saw there's a question. I'm so sorry. I didn't notice. So for the adjacency list, suppose want to forgo the adjacency list for directed or undirected. I'm so sorry. I didn't notice on. Is he still here? So I'm not so sure. One is it looks like one is connected to 4. So maybe from 0 to 4 to 1. Okay. So I had a feeling that what he's trying to say is that I think this is what the reason why he said because from 0 is connected to 4 and connected to 1. Okay, so the adjacency list, you only how do you call that? You only take into consideration the adjacent vertices. Okay, So the adjacent vertices for 0, why is it 0 to 4 to 1? It looks like 1 is connected to 4. Oh, maybe it's the other, this one. Is it? Is this what you're trying to say? 1 is also connected to 4. Yeah, because if you look here in the adjacency list, 1 is connected to 4.
Uh, that one looks like 1 connected to 0, connected to 3, connected to 4 for the row 1. But in the picture, 0 cannot be connected to 3. Or am I
No,
looking at it?
because this one is not 0 connected to 3 to the 4. Vertices 1 connected to 0, 1 connected to 3, 1 connected to 4.
0 connected to 1, 0 connected to 4.
1 connected to
Okay.
0, 1 connected to 3, 1 connected to 4. This is what,
Okay,
this is the thing that it's doing. Because you want to keep track of all the adjacent vertices, not the that one. So it's this list does not mean 1 connected to 0, connected to 3, connected to 4. So this is not how you read the adjacency list. The adjacency list, this is how you read it. 0 connected to 0, 1 is connected to 0, 1 is connected to 3, and 1 is connected to 4. Does that make sense, class? Yeah?
Okay.
Okay. All right, so that is the question for that. I'm not sure why C not choose E. Can visit E from D. I'm not sure which one is that. So just now, if you see how I do this, I did mention that I choose it alphabetical order. You can choose E as well. First, before you choose C. So it's just that because we put it alphabetical order, I determine which note to choose next based on the alphabetical order. Okay, so it doesn't matter whether you want to choose E first or C first, in the DFS or BFS. Okay, because normally for BFS and DFS, you don't really consider the cost, okay, because basically you just want to do the search unless you want to find the shortest path. So if you want to do the shortest path, that's why you apply the Dijkstra. So we're going to be looking at how we can find do the search or the shortest path somehow, in a graph. Is that okay, class? Right?
Okay.
So please attend your tutorial. So I'm going to see for group 1, 2, 3. I'm going to be seeing you Thursday. So for group 4 that is in my lecture, please ask Dr. Raja. So if she has covered or going to be covered the next lecture, maybe perhaps you let me know. I will talk to her. Maybe you can join one of the or one of my classes, okay, so that you won't miss anything for this tutorial. All right, so just check with Dr. Raja whether she has covered this the tutorial for this topic or not. Okay, so if she has and you missed it, you can always join my class. All right. Okay, so in that case, I'll see you Thursday then, right? Let me start the recording. All right. Okay, thank you everyone. Bye.
Thank you, Doctor.
Assalamualaikum. Bye.
Assalam.